Okay, again, welcome to the last part of chapter 26. It's basically we're still dealing with the RC circuit. We have discovered so far on how to charge an circuit. Basically, what it is you have a battery and you add to it a resistor and you add to it a capacitor, usually for safety and basically for control. We have to have a switch of some sort so that we synchronize the clocks and say, okay, at t equal to 0, that's when I'm going to basically click on the clock to start it, starts ticking the seconds. And I want to build charge in my capacitor. I want to fully charge this capacitor. It turns out the charge depends actually on the EMF, epsilon. So the more EMF you have, the more charge you're going to put in the capacitor. It's also proportional to the capacitance. I mean, the bigger the capacitance, the bigger charge you can put in there. As a matter of fact, the numerical value for the charge itself at the end, after basically you wait for a long time, and the current initially starts to build basically the charges. That's why you see the current, but the current over time starts to diminish with time because as the capacitor starts to build charges, it's going to resist additional charges, and basically it's going to kill actually the current at the end. So that's basically what we have seen. The current declines basically decreases exponentially with time. When t equal to infinity or when t approaches infinity, the current approaches 0. The charge at that time would have saturated to its maximum value, which is the capacitance C times epsilon naught, which is the EMF of the battery. So if you have a 12-volt battery and you have a capacitance, let's say, for example, of 1 microfarad, then the maximum you're going to put in that case is 12 microcoulombs. So that's basically how you're going to think about it. Obviously, the value of 12 microcoulombs in this example is really a limit. It's not 100% if you wish, but practically it's reachable, as we saw in the lab, within actually few taus, few time constants. Within 4 or 5 time constants, the value of the charge in the capacitance would have been almost equal to C epsilon. So basically, that's a good enough probably approximation in practice, and we're good. Now we also did calculate in terms of the energy to see exactly what happened in terms of the energy. The energetic of a problem in terms of charging is the following. You're going to build the charge, which means you're going to put energy in the capacitor. And the energy in this case is simply equal to the charge squared divided by 2C, And the C in this case is the capacitance. So if we work out the algebra, since we know the charge at the end is C epsilon, so square that, it's going to be C squared epsilon squared divided by 2C, cancel the C and the C squared, and you will be left with 1/2 of C EMF squared, okay? Then we said, okay, great. We have stored energy in the capacitance. Down the road, if I need it, I'm going to use it. But at this point, I have energy stored in the capacitor. The question then is, excuse me 1 second, let me make sure that this door is locked. The question then is, where did we get the energy from? And the answer is simply, in this case, it has to be the battery, because that's the only source of energy in the circuit. We calculated the energy in the battery simply by going to the concept of power. Power is equal to voltage times current, and we have seen that in the chapter before, actually. And since the power is the rate at which the energy is being consumed or is being dissipated or being basically used, all we have to do now is integrate this power from the beginning of the process, which is t equal to 0 when we turn the switch on, until the capacitor is fully charged, reaches the maximum value of C epsilon. And we know that that time is an infinite amount of time. So we integrated from 0 to infinity of the product of the EMF in this case, because that's we were interested in the energy drained from the battery. So it's the EMF of the battery times the current, which was draining basically the energy from the battery. The integral turned out to give me a value that is twice as much as we stored in the capacitor. Namely, the capacitor had 1/2 of C epsilon squared. Now, in the case of the battery, we took from it exactly twice as much C epsilon squared. So the question was, where did the other half go? So the only suspect in this case was the resistor. So we said, okay, how much energy was dissipated in the resistor? Again, we went back to the same expression for the power, the voltage across the resistor, which is V, is given by Ohm's law, which is Ri, times the current, which is I. So I was interested in integrating Ri squared, okay? And again, from the beginning to infinity, because during the process of charging the capacitor, that's the time it took for us to build that charge in there, that energy there. So we wanted to know how much energy was dissipated in the resistor in the same side. It turns out to be the other half missing. So basically, half of the energy went to be stored in the capacitor's useful energy so that we can use later on. The other half was wasted in the resistor. And that's basically when we add them up, we found exactly how many joules we took from the battery. So that's basically what we did last time. Now we're going to look at the problem from the second part of it, which is discharging the capacitor. So at this point, we don't need another power source, because if we do have a power source, it's going to probably build a charge. I said something wrong last time, and I really am sorry for it, because I was not, I mean, we were during the lab actually. The signal there, if you notice, at some point we have a positive EMF, and at some other point we reverse it. Actually, we manually reverse it to become a negative epsilon. So in this case, what happened? When it's completely reversed, I already have about 120 volts across the capacitor. That is basically the maximum voltage I will get from a 120 volt battery when I'm charging it. So if we wait for a long time, that's the voltage across the capacitor. When I reverse the battery, now I have 120 volts from the battery pushing with the 120 volt from the capacitor, a current that must be very high in the beginning, because I have 240 volts basically working together, trying to push the current. So the current will be extremely high. So the total drop of voltage, that is the sum of this, what is equivalent to two batteries really, running at 120 volt each, should all of it happen across the resistor. And that is correct. So the numbers were correct. When we measured the voltage there, it was extremely high, around 200. I think immediately after we turned the time on, it was 225 or something, at least my simulation. Probably yours was close enough from there. So that is expected. There is no problem with that. But now the battery is discharged not just by its own, which is true. It's going to discharge on its own. But also it's being helped by the battery that is pointing in the opposite direction. So it's pushing more charges away from it because the current is so extremely high. So in this case, what's going to happen, the capacitor will lose all of its charge. So the voltage across it drops to 0. But that's not going to end there. So the current is not going to die there and there. It's going to continue in the same direction, because there is a battery also still pushing charges. So in other words, if this was the positive side of the capacitor in the beginning after we fully charged it, and this is the negative, when we reversed the battery, this side that was negative will go to 0, and the side that was positive will go to 0. But the negative side now starts to build positive charges. So there is another cycle of charging again. That's what I missed last time, because I was basically trying to rush through things. So that is the part that you need to be very careful with. So when you wait for a long time, when you reverse the battery, the current will ultimately drop to 0, because at the end, the 120 will be reversed now in the capacitor, which will kill the current at the end. And it's not going to happen. The current, basically, the voltage is not going to be 0 at that time. It's going to be minus whatever it was before. So if it was positive 120 volts, now it's going to read negative 120 volts, because now the capacitor is charged in the opposite direction. So that was something that I said there. So today, what we're going to do is we have charged basically the capacitor using the battery. And we're going to take the switch from the A position now and immediately turn it to the B position. In that situation, what we have, actually, we don't have the battery completely. It's out of the picture. So that is not like the lab. It's unlike the lab in a sense that the battery, the capacitor is discharging on its own. It's not being helped by the battery. So that is a distinction you need to make between the lab and the theory that we're going to do today. Furthermore, the theory we did on Monday, actually, for the calculation of charging the capacitor, we assumed that initially there was no charge in the capacitor. There is no restriction on why we should have that. We could have had an initial charge in the capacitor and work with it. So if the initial charge happened to be positive already in the positive side where I'm building charge, I don't need as much to charge the capacitor. But if it was negative, I have to first of all cancel the negative and then build the positive on it. So basically, that is the process. That is actually the second part, if you wish, of the lab that was happening in that situation, because there was already a charge and it was actually fully charged when we reversed the battery. So the battery's role now first is to cancel the charge and then build the charge in the opposite direction. What was negative side becomes a positive, when what was positive becomes a negative. So again, the math also will support that scenario if we really were careful enough. There is no problem with it. It's just the initial conditions for the integral, that's all. The integral, basically, we were saying that there was no charge in the beginning, and that's why the constants at the end turn out to be C times epsilon. If not, it's going to have an additional Q naught, which is the charge in the capacitor to begin with. But Q naught, there was nothing, actually, in our case on Monday. So I hope that I clarified that issue a little bit. So let's share the screen and see where we are in terms of last time. If I can find where, oh man, the circuit first. So this is the power, this is the stuff we did last time. I hope you guys are taking notes and going through the calculations again. Don't trust what I do in here, because sometimes I make mistakes, and I trust that you guys will correct them, or at least let me know. So right now it's fully charged, basically. The battery and the capacitor are fully charged. We're going to switch it to portion B. For that, I'm going to have a new drawing, okay? For that, I'm going to have a new, fresh start at this so that we have a clearer picture of what's going on. So this is what we're saying now. I have a circuit that looks like this. I have a resistor R, followed by capacitor C. And usually, for good, basically, measure practice, you have a switch, now it's closed. Initially, that is a big deal. There is a charge in the capacitor. And the charge in the capacitor, I'm going to take it to be positive on this side and negative on the other side. It's clear from this picture that the current will flow in this direction. It's going to flow counterclockwise. It's going to go like this, to go from the positive side of the capacitor through the switch, which is closed at this point, and to the negative side. Okay, since I have already charge, positive charge sitting in that side. And it's going to continue doing so until at the end, I have discharged the capacitor. And at the end, all the charges will move to the other side, the positive charges, and I'm done with it. There is no other way. I mean, it's not gonna, it's going to end at that point, because the capacitor is not going to change its mind and push charges in the opposite direction. It's not a battery. The current I in this circuit at some time in the future, so this is a time-dependent process, not at t equal to 0. This is I later. At t equal to 0, I is equal to 0, actually. And Q is equal to Q naught, okay? So that's the situation for what we have. So this is at t equal to 0. In the future, Q will not be equal to Q naught. It's going to be less, actually, than Q naught. And the current will be something that is draining the charge from the capacitor. So this is basically, in a nutshell, what the physics look like. So the relationship between the current and the capacitor and the charge now is kind of different a little bit. We know that the current is usually the rate at which charge change, or at least the rate at which the charge change. But in this case, I'm going to take a minus, and let me tell you why the minus is needed in this case. The minus is needed because this current is not building up charges in a capacitor, but it's actually, this is the rate at which the capacitor is being discharged. So this is the rate at which the capacitor is being discharged. So the word discharged in this case, the prefix dis in this case is the minus sign. So in this case, if I do everything this way, everything will turn out to be positive. I could have been completely ignorant about the physics and did just this problem as if it's a mathematical problem, and you will have some textbooks that do that, okay? What they say in this case, okay, when you switch back to AB, from A to B, hey, keep the direction of the current the same. Keep the direction in this direction, keep the charge Q on this side, and keep charge negative Q on the other side, and use Kirchhoff's rules in this case. If you follow from the starting point in here, let's say, for example, before the resistor. So in this case, what happened? There is a drop of voltage across the resistor of Ri, plus a drop in voltage across the battery, which is Q over C, and the whole thing equal to 0. And you ask yourself, what is the relationship between I and Q there? It's simply the same relationship that we had it in there, because now it looks like the current is putting charges on the capacitor, as you can clearly see from this picture. So I, in that case, is dq over dt, and you solve the problem, and that works. But then at the end, when you do the derivative for the charge to find the current, you're going to have a negative number. And that negative number tells you that the current, that the direction of the current you chose is not in that direction. It's in the opposite direction. And this current actually is discharging charge from the capacitor. We could have followed that rationale, basically, or we do it basically understanding of what the physics is. So we could have found, basically, we could have followed a purely mathematical approach, saying, okay, we don't know the physics. We're going to discover it down the road. And it's true. You're going to do that. You're going to arrive to the answer. Or you can say, you know what? I know what's going on. I know that this situation, I don't have any battery now. So the current must be flowing from the positive side of the capacitor down to the negative side of the capacitor. And this current is a current of discharge. So current I must be related to the rate at which the charge is dropping by this number. So I is minus dq over dt. And we'll arrive at the same conclusion, basically. Except the current now will be on the positive side because I know exactly which way it's moving. So if I choose it like the green side, like I did in the beginning, it's going to be positive. So if I choose it clockwise, it's going to be positive. And the problem, there is no problem with it. Everything works. So since I'm choosing the current in that direction, and it's a good practice always to do your loop equation in the same direction as that of the current, that way you don't have a problem with the resistor. So there is a voltage drop. What I'm saying in here is actually where the voltage drop is. It drops from here down to there, and that drop is Ri, okay? And if we did it the other way around, like we did with the red marker, actually we were saying the drop is the opposite. But when we do the calculation, actually we'll find that this is the actual drop. The mathematical approach at the end will yield the physics, okay? Because this is the actual drop. Since it's dropping, the current is coming from this side to that side, so it must be dropping in that direction. So hopefully you guys are not confused about this last point. If you are, take this approach, and if you want me to, I can do the math approach also, and whichever you're comfortable with is fine, okay? If you like the math approach completely as if you're ignorant about the physics, that's fine. If you want the physics one, which is actually more sound in my opinion, you're going to get the same answer in either case. Okay, so I'm going to take the same point, starting point, because I always like this side of the circuit always. But now I'm following the current, so there is no drop in voltage whatsoever because this switch now is just a zero resistor. So now when I come to this side, I'm coming from the negative to the positive. So I'm actually rising in potential. So in this case, it's a minus Q over C. Remember, the equation counts the drop. Since I'm rising, so I'm dropping, if you wish, by a negative number. Okay? So that is the drop in voltage across the capacitor when I am going in that direction. Plus, of course, the drop in the resistor now, which is Ri. This whole thing equal to 0 because I don't have anything else in the circuit. So once I hit this point in here, I drop by negative Q over C, and then I drop by an Ri because I'm in the same direction as the current. The only reason why I put a minus because I notice immediately that I hit the negative Q in here and positive Q in there. So actually it's a rise in potential. okay? But again, since I'm counting just the drops, this is a minus drop, okay? If you agree with me in this equation, then we're in business, because I have already I equal to minus dq over dt. So this equation becomes minus q over c minus r times dq over dt. And the whole thing is equal to 0. Obviously, since I have a negative sign everywhere, I'm going to just rearrange my equation. And it's going to give me the following. So if I take this side to the opposite side, I will have q over c equals to r, I'm sorry, negative q over c equal to r dq over dt. Multiply one side by dt and divide by r. So the equation then, and divide by dq also. So basically rearrange this expression to the following form: dq over q is equal to minus dt over rc. Okay, I'm supposed to integrate this expression, trying to find the, because I'm trying to find I as a function of time and q as a function of time. So I need to find the antiderivatives of this expression, okay? Again, this is similar to last time. The integral of dq over q, which is just the integral of, except that I had it shifted last time. I was dealing with q prime. This is q, actually, the integral of dx over x, which is the same thing like before. So this must be also a log of some sort. So this is an ln of q. I'm assuming q to be positive all the time, and we'll find it to be positive all the time, okay? Equals to minus the integral of dt over t, which is just t in this case, over rc, plus a constant, okay? That's the antiderivative. Now, of course, I don't like this ln business, so we're going to exponentiate everywhere. So on one side, we'll find q as a function of time. On the other side, the exponential of the sum is the product of the exponentials. On one side, it's the exponential of a constant, which is another constant, not necessarily that same constant, times the exponential of negative t over rc. We really have to find what that constant is. Well, we know what happened at t equal to 0. At t equal to 0, the charge was q naught. So q, when t equal to 0, was q naught. So all I have to do is sub in this expression by 0. So it's going to be the constant times the exponential of 0, and exponential of 0 is 1. So the constant itself is actually q naught. So q sub t then is going to be q naught exponential of minus t over rc. Here we go again with rc. It's the same time characteristic. Actually, the symbol for it, and we did that in the lab, is tau. So this is one of several time characteristics that we'll be dealing with in this course. This is rc. The units for this must be also second, okay? And it's a good practice always whenever you do a new math problem and we're solving problems. Excuse me 1 second. Whenever you're solving one of the problems that you have in class, it's a good practice to check the dimensions, because again, this is something that you should have done in the first day when you guys met in physics 4A. And the idea is dimensional analysis. Dimensional analysis. Okay, let me ask you again. Did you guys remember doing that in physics 4A? Dimensional analysis.
No, I don't remember.
Are you serious? This is the first thing when you do units. Anybody else remember that, maybe, hopefully? Other than Christopher?
Does it have any other names, or is it labeled something different?
When you do MKSA and you do dimensions, basically, for example, F equals to MA is a force on one side, which is kilogram meter per second, times, kilogram meter per second, and you do come up with a new equation. Then that equation, you do dimensional analysis. Here is the deal with dimensional analysis. You check an expression, okay? And if it does not pass a dimensional analysis, you know that you're wrong. You know whatever you did up to that point is completely nonsense. Then if it passes the test, you know that you are not wrong. It doesn't mean you're right, but it means that you are not wrong. Because you don't remember this discussion you're having it with the physics?
Yes, we did do it.
Okay, great.
I think they presented it as like units of measurement. Like you're,
Units of probably that's what it's called. I'm sorry, probably I
yeah.
use different
No,
terminology.
it's okay.
Okay, so let's do that in here too. Okay, the reason why you might be wrong is because of the fact that you could be having a factor of 2 pi or a factor of 3, and there is a famous thing that physicists do all the time, and it's called chasing after pi. You solve, you go through several pages of calculations, and at the end you find that you have either an extra pi or you have you're short of 1 pi. So what you do in this case, you start all over again calculating things, trying to find where the pi was missing. So that's what it is called. Sometimes it's called chasing after pi. So basically, the point in here is that you could have the expression that is correct dimensionally, but again, probably you have a factor here and there that is off, probably. Okay. That's why they say that if you do dimensional analysis and if it's wrong, that's it. It's gone. It's no good. No, you have to do everything all over again. If it's right in dimensional analysis, doesn't mean that you're right. At least you're not wrong. So that's what we need to really do. This is a time. It has to be measured in seconds. So I want to make sure that whatever we're doing in here is correct too. And I want to have this also. You remember, I'm trying to build an arsenal, basically, tools for you guys to enrich your discussion at the end. This is one of them. Does it make sense? Okay, you run a dimensional analysis, you find that everything matches. At least it's not wrong, okay? At least you're on the safe side when it comes to that point. So that's really one of the things that I'm looking for. I know we have mentioned several things so far. This is another one. So the unit for tau, I expect it to be second. Okay. So, and it's the units then for R, which is ohms, times the unit for C, which is coulomb. I'm sorry, it's a farad. So technically, is an ohm times a farad a second? That's basically what the question is. So an ohm, for example, there is an expression that I can run into trying to help me, which is V equal to Ri. The voltage is equal to Ri. Okay, that's one way of doing it. So I can say that the ohm is the units of the voltage, which is V, over the units of the current, which is ampere. That's one way of doing it. Well, also the units for the capacitance, I can use the same thing, which is Q over C is also voltage. So the units for the farad are the voltage, is the voltage, Q over C, I'm sorry, did I, Q over C is equal to a voltage. That means the units of the C are actually, I'm sorry, it's not voltage on top, so it's the coulomb from this expression. It's the coulomb divided by a volt. So this product then is that of a voltage of an ampere times a coulomb over a voltage. That's good because I don't care about the voltage, which is actually not a fundamental unit too. But the coulomb and the ampere are related. Remember from this expression up? That's one way of saying it. That the coulomb, I mean the ampere, is simply a coulomb over second. Okay? So second from this expression, because this is the derivative of Q, which is a coulomb divided by the second, which is a unit of time. So in here, the coulomb then is nothing but an I'm sorry, the second is a coulomb over an ampere. That's exactly what I ended up with. Coulomb over an ampere, which is exactly what I wanted, which is a second. So dimensionally, this expression makes sense. So basically, you go back to the fundamental expressions that you know. In this situation, both Ohm's law, this is Ohm's law, by the way, and the definition of the capacitance, which is here, give me both ohms and also the farads. Use those. all of a sudden the voltage cancels, and I end up with a coulomb over an ampere, and that is exactly how the current was defined. Was the rate at which the coulomb changes with seconds. So all I have to do is divide by an ampere, and now I have a second, which is just a coulomb over an ampere. So it checks. It's a good practice always to check your expressions, especially when you go through a very, very lengthy calculation and you have a bunch of terms all over the map, okay? Then in this situation, it's a good practice to actually do dimensional analysis because it might save you a lot of headache down the road. If you plug in the numbers and things start to they don't make sense, you could have prevented all of that headache just by doing dimensional analysis, and you know that your expression that you calculated is wrong. So you have to go back and fix the problem, okay? As I said before, and this is something that probably whoever gave you for A has already emphasized this point. Once they match, like in this situation, it's a second on one side and the second on the other side. It doesn't mean that it is correct because you could be off by a factor of 2, for example. This, if I found that 2 RC is a time characteristic, that also checks as a second because the 2 has no dimensions. But in this situation, it's exactly equal to RC. So again, here is a time constant for this problem, which is exactly that of the charging capacitor. So the expression then we end up with for the discharge of the capacitor is Q as a function of time is equal to Q naught exponential of minus T over RC. Okay, I want to keep it for right now, this expression. Oh man, sometimes this screen, I think there is probably something wrong with my screen. Okay, there are missing paces in there. So minus T over tau. Let's try to find the current. The current, as I said in the beginning, we took this route. It's minus dq over dt. And the minus is exactly what is needed to cancel this minus when you take the derivative. So it's going to be a positive number of q naught divided by tau exponential of minus t over tau. Okay, remember tau is RC. So that is the current then in this situation. It's positive because I took that direction to be positive, so everything fits the bill. If I did the problem the original way, that way I was telling you guys, I mean, not original way, another way, like some textbooks do, and that is through the red direction, everything will say works. I mean, everything still holds true. You're going to have a drop in voltage by Ri across the resistor, written in red, plus another drop in voltage Q over C, and the whole thing comes back to 0. You integrate that expression, and it's exactly this integral too. It's going to give you this exact answer. What is the answer? The constant times exponential minus C over RC. Then you equate the initial conditions and you're fine. The trouble with it is when you find the current I. The current I now have this derivative because it's simply in that situation dq over dt. And it's clear from this expression it has to be dq over dt because that red current is still building charges in the capacitor. So this is the rate at which charges are building from this schematic with the red one. So it has to be dq over dt. But then when you take the derivative, because of that minus sign in the numerator and the exponential, then you will have another exponent minus in here. So this term will have a negative, indicating to you that the current, the one that is in red in my picture, is actually in the opposite direction. And what you thought was actually a drop in voltage was actually a rise in potential. When you thought that this is actually a drop in potential, was a rise in potential. So the math then dictates to you the actual physics. So the math, you follow this approach and you say, I don't know which direction it is, so I'm just taking a random direction, just continuing in the clockwise direction. And I think this is, if that's the direction, then this is actually the drop from this point down. So that's the voltage Ri. And there is another drop Q over C. And you follow the calculation, I will turn out to be negative, which means that what you thought was actually a dropping in voltage was actually a rise in potential, and the whole physics holds true. Okay. So now actually you're discharging the capacitor. So if you wait long enough, it's going to discharge. So in textbooks take that approach. I prefer, honestly, the second approach because of the fact that I'm taking the physics into account. because I know what's going on in this situation. There is no other source of power, so I know exactly what's going on. And it's up to you. You could do both, okay? Trying to convince yourself that, okay, here is works, the other one also works. Again, it's never end over until you actually do an energetics in here, okay? So you ask yourself, obviously, if this was a switch AB, Q naught, I know exactly what it is. Q naught is the last charge that was built in the initial case, which is C epsilon. So this number then will be C epsilon over, yeah, C epsilon over RC. The C's cancel and we're back to the same expression as before. But you don't have to be. It could be any way that you have charged your capacitor. Q naught is Q naught, okay? So we're going to take about and talk about the energy. Okay, again, we really nothing matters that you do in physics, honestly, unless you have a full account of how much it costs, and it only costs when you start talking about energy. So let's see what's going on in this situation. At t equal to 0, there was an energy in the capacitor, and this is how much energy was. 1/2. I'm sorry, this screen is. It's not. There is no problem. I think sometimes it works. 1/2 of Q squared, actually, not, that's how much charge was in the capacitor, divided by C. So this is at t equal to 0. When I wait a long time, the exponential goes to 0. This exponential goes to 0. When t goes to infinity, Q goes to 0. Because you can clearly see the exponential decays exponentially. So it's going to be 0 after a long time. So there is no energy left in the capacitor at the end, because we don't have any energy left at all. So when t goes to infinity, the energy in the capacitor will be exactly 0 because there is no charge left in the capacitor. So again, the question is, and this is hopefully now you know the answer to it, and that's part of your discussion at the end. In the case of the discharge of the capacitor, the energy in the capacitor after a long time will basically disappear. So the question is, where would it go? Where do you think the energy must have gone? Ask yourself, what are the elements in the circuit now? We don't have a battery anymore. I need help in here. Okay. Anybody else? So we had an energy which is 1/2 of Q squared, Q naught squared over C initially, okay, in the capacitor. We have the resistor connected to it. We have a switch, which basically has 0 resistance, and we have wires, okay? And at the end, when we wait long enough, we know there is no energy because at the end it's going to be 1/2 of 0 squared over C. 1/2 of, yeah, 1/2 of 0 squared over C. So there is no energy at the end because Q will go to 0. So where do you think the energy has gone then? Anybody?
Is it lost to the capacitor and the wires?
The capacitor is the one that has charge in it.
Oh, okay. So
So
no.
we'll so we lost energy from the capacitor. The capacitor has charge, and the capacitor now lost all of its energy because it lost all of its charge. So just what are the culprits? Heat where, Daniel? There is specific components in the circuit that must have done that. I mean, you're probably correct in terms. So that's correct, Alexander. Okay. So that is the answer. So usually when you have losses of energy somewhere in the circuit, you have to suspect the resistors. Actually, there is a problem. I don't know if I assigned it to or not, part of the homework assignment, where you have actually capacitors in one configuration and they have energy. You can calculate the energy. Okay, I think they were all in parallel. But then when you take them, the same capacitors, and you connect them in series, the energy drops. Okay, so you ask yourself, where did the energy go? There are no resistors there. So the only culprit again are the wires. It must have gone in the form of heat, like Daniel was saying. But in that case, since you don't have any resistors, that energy must have gone in the wires, because ultimately this is a practical problem. So practically, yes, the wires will have contributions. The junctions also. The switches actually have finite resistance. Everybody has a finite resistance. As a matter of fact, the battery also have a finite resistor, and so is the capacitor. So everybody will contribute to these losses. But the biggest culprit in here, the biggest player when it comes to that is, since you have a big resistance in there sitting there, that is where the heat is lost. So this is your point of discussion this afternoon for your for the after class. So it's in the resistor. So let's find now. So this is how much energy we have in the beginning. This is how much we had to begin with when we started the process. We had this much energy. We know we don't have anything at the end when we're done. So the question is, we're suspecting it's all went into the form of heat, joule heating actually, in the resistor. Okay? And how much it must be? It must be that same quantity, 1/2 of Q naught squared over C. So let's find out. Let's see if it's indeed true. Remember, the expression for the power across the resistor is just the voltage, which is Ri, times the current, which is I. So this is Ri squared. Actually, as a matter of fact, this is sometimes people memorize this expression. This is the power. This is in watts. This is not in joule. It's in joules per second, if you wish. So this is a rate at which energy is being dissipated. So we want to find the energy. All we have to do is integrate this expression from the beginning to the end. And we're saying this time was an infinite amount of time. This whole process from 0 all the way to infinity. So I better integrate. I better sum up from that starting point to when we're done with this. So the energy dissipated in the resistor must be then equal to, there is no parenthesis in here, it's not time dependent, the integral from 0 to infinity of the power dt. Because the energy in this case is just the power is just the derivative of u with respect to time. And I have the expression for I, which is given by that exponential. With this expression, all I have to do is square this number and integrate it. So let me remind you of how I really is. I, as a function of time, is Q naught over tau. Tau is RC times the exponential of minus t over tau, and tau is again RC. Okay, I'm going to square this number. When I square I, in this case, when I square it, I square this number, and I multiply in here by a factor of 2. Okay, so that's basically the integral I have to carry in this case, times, of course, R. So the energy that is dissipated in the resistor is R times this one, integrated from 0 to infinity. So it's R times Q naught squared over R squared C squared exponential of minus 2t over RC, of course, with respect to time. Okay. R is constant. First of all, there's a cancellation in here, R and squared. And Q naught squared over R C squared is constant. So I'm going to take that as a outside of the integral. So it's going to give me Q naught squared over R C squared. And then the integral of the exponential, I have a 2 in here, RC dt from 0 to infinity. The 2 is coming from the square. So when I integrate, all I have to do is divide by the coefficient of t, which is 2 over RC. That means I multiply by RC and divide by 2. And then you have the actual integrand. So in this case, Q naught squared over RC squared times minus, don't forget the minus, RC over 2. And then the antiderivative of the exponential is the exponential itself, which is exponential of minus 2t over RC. And the value is between 0 and infinity, okay? Cancellations in order in here. The R cancels the C squared cancels the C, and now I'm left with negative Q naught squared over 2C. I'm left with one of the C's in the denominator. Exponential at positive infinity, it's 0. At 0, it's 1. So it's 0 minus 1, which is a negative 1 times a negative, it's going to be positive again. So this is going to be positive Q naught squared over 2C. This is how much energy was actually wasted in the resistor. So this is lost in R. And where did this energy come from? It must have come from the capacitor. This is how much energy we started with. 1/2 of Q naught squared over 2C, which is exactly the amount of energy that was lost in the resistor. So it checks. Okay? So in this case, both of them check. The resistor and the capacitor, they check. So they say, basically, this is what the discharge in this case of a capacitor. So to give you an idea of this whole thing, this is basically what went on. So when we had the switch in position A, we were building charge. Charge in this case, we wait for a long time. Practically, you don't have to do that. You can wait probably for 10,000. You're going to have 99.9999 something good enough for the problem. And you say, okay, now it's fully charged. Now I'm going to switch it back to position A. I'm going to say position B. In this case, it's unlike the lab where you actually have to reverse the battery. In this case, no, you cancel the battery altogether. Now you have an initial charge Q naught. That Q naught at the end, you wait for an infinite amount of time, it's going to disappear. So this is how the graphs look like. In terms of Q first, okay? I'm going to take C epsilon as being my Q naught for the second cycle. So I had a battery. So this is the voltage across the capacitor. This is unlike the lab, by the way. The lab was looking for the voltage across the resistor, which is just the current because it's R times the current. So this is the voltage across the capacitor. This is time. This is the asymptote. So if I wait for a long time, the capacitor will basically almost be equal to the asymptote. And this asymptote actually is C epsilon, where epsilon is actually the EMF of the battery. Okay. Now, this is when the switch was in A. When I switch back to B now, remember now, so the times are different, okay? So when I switch the back to B, the clock resets. So we're back to T equal to 0 again. So I can put the two graphs on top of one another. But you have to understand that that's actually a different timeline. So it happened in the future of the first event. So now it actually decreases exponentially until it approaches 0. It starts from that value and starts to decrease exponentially. So this is when the switch was in B. But you have to understand that the clock resets when you go from A to B. So you're going to click on the chrono and make it back to 0 and then start all over again. So that's basically how the graph for the voltage look like. I mean, yeah, for the voltage across the capacitor look like. For the currents, okay? Initially, both of them are going to be the same thing, by the way, for the current. Whether in A or B, both of them are going to decline with time. So initially, it's the EMF over R. Even in this case, it's the EMF over R because it's Q. What is the expression for the current in this case? Q over tau. Q naught over tau. So that's the expression. But if Q naught was C epsilon and tau is CR, the C's cancel. So I'm back to epsilon over R. So The initial current in both situations is epsilon over R. All the current is actually across the resistor. So this is I as a function of time. In both cases, it's going to decrease exponentially with time. Whether I have it in that situation or in this situation, this is basically both of them. Now, if I follow the mathematical approach for this problem, I have to actually put it with a negative sign because I have it in the wrong direction. So the graph will drop below the x-axis, but that's not the concern in here because I can fix it and put it back up like I'm doing right now, like I did the problem the way we did it in this situation, okay? So this is the current, whereas this is the current for the entire circuit, by the way, for the circuit. Across R, if you like, okay? Because that's the circuit. And this is the voltage, but this voltage is across C, the capacitor, okay? So that's basically how this behavior is in terms of the curves, okay? Okay, how to solve problems. It's very critical to remember the following when you're dealing with an RC circuit. Usually, in the problems that you have in this chapter, okay, either immediately after you turn on the switch, they ask you questions. How much is the current in the resistor? Well, in that case, immediately after t equal to 0, I mean, t is very close from 0, okay? Immediately after t equal to 0. Immediately after, not before, not during. Okay? The capacitor looked like this. So if this was a capacitor in a circuit, if this is the actual drawing, this is how it looks like. It's like a wire. Okay? It's short-circuited in this case because it will allow all the current to flow through it. Okay? Immediately after. Now, if you wait for a long time, okay? So it looks like a switch that is closed. So this is how it looks like then. Switch that is actually closed. Now, if t is infinite, you wait for a long time. And a lot of problems they tell you after a long time, we wait for a long time or a long time after or something like that. When you see that word, you know that you can assume that t is infinity. So the capacitor, again, it has a specific drawing in the circuit. Looks like this. The way you replace it in this case is a switch that is completely open. Switch in the off position. There is no current in here in it. I equal to 0. That's what that means, okay? So if you have problems, and you have problems already, and they tell you we wait for a long time, that means there is no current flowing through the capacitor. End of the story, period, okay? So you're done with it. It's fully charged, and it will cancel any current trying to go through it. End of the story. I mean, you might have other current somewhere else. Let me give you an example. Let's say, for example, I have this resistor connected to this resistor, and probably I have a battery in here. And in here, I have a capacitor and this resistor, okay? Call this one R1, call this one R2, call this one R3, and this is a C, okay? Immediately after, this acts like a wire. So the circuit would look like this immediately. The circuit, the same circuit that I drew there, is actually this one. You have a resistor R1, you have a resistor R2, you have a resistor R3, and that's it. Okay, so this is R1, this is R2, and this is R3. The capacitor doesn't, it's just a wire. Replace it by a wire, that's it. Okay, but this is immediately after your switch I mean, after you start time. After there is a switch somewhere in here. I forgot to draw it. But let's say, for example, there is a switch in here that you close, okay? So immediately after that's closed, that's basically what's going on. That's how the circuit looks like. The capacitor doesn't exist in this case at all. So you can calculate the current, which is very easy in this case. If you're interested in current through R3, then in this case, it's fine. R3 is just given by, okay, the R equivalent for this case is R1 plus, what is it? R2 times R3 over R2 plus R3. So that's R equivalent. This is the whole thing. multiplied by the current should give me the EMF. So this is the total current here. Okay. Well, in order for me to find this specific current in here, then I know R3 times it's the voltage across it. It's basically this minus that. So let me do a quick calculation in here. So it's this voltage divided by R3. So I'm gonna, without doing any simplification, so it's the EMF minus this current, R times R1. So it's gonna be R1 over R1 plus R2, R3 over R2 plus R3. And the whole thing, I'm sorry, the EMF, I didn't take it out. So this is the EMF across R3. And of course, all I have to do is now divide it by R3. And this is the current in I3, if you wish. Okay, this is immediately after I switch put the switch on. Please do verify the answer if this is the circuit that you have. Okay, it's a good idea to throw in numbers in there just to see how this looks like. For example, let's make this one 12 volts, and this one is 10 ohms, and this one is 5 ohms, and this one is another 10 ohms. Okay. And we're interested trying to find the current through this 10 ohms, the second 10 ohms. Then in that case, it's very easy. I have in here, both of them, I have, what did I say for the EMF? 12? Yeah, I think I said 12. So I will have 12 times 1 minus the ratio of R1, I think it's 10, divided by R1, which is 10, plus, what is it, R2, which is 5, divided by, I'm sorry, 5 times 10 divided by 15, okay? And divide the whole thing by R3, and R3 is 10. So 10, so it's gonna be 1.2 times, let me find the answer in here for you guys because it's some, let me get the calculator going in here, okay? It's a good idea that you do the calculator also from your end. 1 minus 10 divided by, open parentheses, 10 plus, not even looking at the expression, 10 plus 5 times 10, which is 50, divided by 15. Okay, close the parentheses. And the whole thing is times 1.2. I don't know if the calculation is correct or not, but I'm hoping, if not, verify this number is okay for me, okay? It says it's 0.3 amps. It says this whole thing is 0.3 amps. Okay, so when I plug in the numbers is 0.3 amps. Yeah, okay. So that's basically, so somebody has checked it too. Okay, very good. Thank you, Christopher. So the idea in here is this is the current, if the number is in there. Now, the second question asks, you wait for a long time after the switch is closed, how much is the current through R3? Go back to the original circuit. Well, this is an open circuit now. There is no current equal going through this area at all. So I3 is 0. If you wait for a long, long time. If you are curious trying to find how much is the current through R2 though, R2 initially had a value and at the end it's going to be a different value. So let's find it. So we need to find for this example again, we need to find the total current. So we already know that this is 0.3 amps. This current through the entire circuit must be greater than 0.3 amps. So I here must be more than 0.3 amps. That's how you make discussions again. So whatever I do now, it should be more. And it should be simply the EMF divided by the R equivalent. And the EMF is 12 divided by the R equivalent, which is 10 plus 5 times 10, which is 50 divided by 15, which is 5 plus basically 10. Okay, so it should be more than 0.3. Let's make sure it is, okay, because I didn't actually do the numbers, so hopefully it is. So I is 12 divided by 10 plus 50 divided by 15. So let's see how much that is going to be. That's the I total, okay, not the I through the R2, okay? So it's 12 divided by 10 plus 50 divided by 15, and this whole thing is 0.9 amps, thank God, okay? we would have been a disaster in here if we find it less, because we would know that we are wrong. It doesn't mean that I'm right, okay? It means that we are not wrong. So I need you to verify these numbers, okay? Because it's more than 0.9, 0.3. So if you are curious trying to find how much current through this resistor, it's simple. 0.9 minus 0.3. So that's 0.6 amps. So I2 then is 0.9, the total current, minus the 1 through the R3 that we just found it to be 0.3. So it's going to be 0.6 amps. Now, they ask you how much current is actually going when the capacitor is when the switch is long time has been closed. So this is immediately after, because there is still current in through R3. But when R3 now doesn't exist, the circuit actually looks like this when you wait for a long time. It looks like you have a battery, you have R1, and you have R2, and that's it, because there is nothing. It's open from the other side. So you have R1, and you have R2, and you have a 12 volt in here, the EMF. So the current in this case through R2 or R1, it's the same one, is simply equal to the EMF divided by the two resistors in series with just their sums, R1 plus R2. So in this case, this is 5, this is 5, that's 10. So the current in this case is going to be 12 divided by 15, and 12 divided by 15 is
0.8.
0.8 amps. Very good. Okay. So the initial current through R2 was 0.6 amps. If we wait for a long time, it's going to be 0.8 amps. Okay. So not all current decrease, by the way, by time. Okay. So this current specific to R3 decreases. It was 0.3 amps. And if I wait for a long time, it's going to go to 0, because there is a capacitor being charged next to it in series with it. But the other currents, they don't have to do that. The total current was 0.9 in the beginning, and it starts to drop and it sticks at 0.8, from 0.9 to 0.8. This was 0.3, and it drops from 0.3 to 0. This actually was 0.6, and now it has jumped up to 0.8. Okay? So you see, this is how you think about problems like this one when you're solving them. The physics in here in terms of charging and discharging capacitors and the relationship I was drawing, and basically we're going and talking and all of that, it just have to do with the RC being in series with one another. So this whole discussion when you're doing it when they are in series with one another, and that holds true for the capacitor in this situation and this R3 and only this one. So what's going on between R1 and R2 has nothing to do with it. I mean, it's related because Kirchhoff's rule still hold. Conservation of charge and conservation of energy still holds. So they're tied up in that sense, if you like, but not through necessarily this discussion of this exponentials and all of this basically nice looking graphs and everything else. So you have to really analyze. And if somebody wants to give you a really hard time and trying to make you really sweat, and maybe you had hate him so much, he's trying to tell you to find I as a function of time, not necessarily immediately after you close the circuit, or not necessarily when you wait a long time after completely discharged. So then, and it is possible, okay, especially if you're going to take electronics or electricity, that's a problem that you have to deal with, okay? And you will have algebra with some differential equations, albeit these are simple differential equations to deal with. I'm hoping that all of these examples we do in class that you go back and revise them, because this is an important example. I think this is one of the homework problems. If not, it's one of the problems that are in the circuit in there, and the book in there. So it's not necessarily these numbers. These numbers, I just put them myself for my own convenience. But hopefully you guys can go and verify the numbers in there and make sense to you. Okay. So this is up to chapter 26. We're ready for the exam. Come Monday, we're going to go through all of those review problems, which are due this Saturday, by the way. We're going to go through them. So I'm hoping that you guys come Monday, the first session, that you bring your questions with you, that you looked at all of them, that you think that this is easy, this I have questions for, I want to know how to do this. This is, I think I am okay with it, but I don't think that I am. This 3 or 4 or 6 of them, they are completely difficult, so I really need to understand them too. So basically, probably you will have 1 or 2 that you don't want to discuss, but we're going to go through all of them regardless, okay? We're going to go through all of them, have a discussion through them, and meet again in the afternoon during the lab session to make sure that there is nothing left to chance. So you'll have the entire day of Tuesday basically going through them. Come the exam time, I'm hoping that you're going to basically have no difficulty with it. Okay, so that's one thing. The other thing also, this closes the book on the basically this exam. I mean, in terms of content, the next chapter is going to be chapter 27. I don't think that we're going to start it until the ninth week, which is the week after the next week, and it's all going to be dealing with magnetism. We're going to discover the magnetic field. We're going to discover basically the how to find the magnetic field, how to quantify it. We're going to discover the concept of motors, where you're going to be basically at some point probably we'll build our own motors. So I'm hoping that you guys will have that chance to do that. And then chapter 28 will continue dealing with the Ampere's law and Lenz's laws, and also chapter 27, I forgot to mention that we will have a version of Gauss's law in it, which is very simple actually. And then chapter 29 will deal with Faraday's law, Faraday's law, yes, and Lenz's law, and we will be ready for exam 3 after that. Okay. So if you guys don't have any questions regarding this content stuff, I know that you're going to be working on this, preparing for the exam, doing the actual quizzes. And if you have any questions, please let me know. Meanwhile, I'm going to be creating different versions of your exam so that each and every one of you will have different exam. Okay. You don't have any questions? See you guys
Uh,
Monday. Yes, go
Professor,
ahead. Yes.
the chapter 25 discussion that's due today,
Uh-huh.
it doesn't have a video associated with it.
The video I did not upload it. Hold on, let me check. Why I did not upload it? That's bad. When was the chapter? Was it last week or this
It
week?
it was last week, chapter 25, discussion part 2.
Oh man, that would have been bad. I thought I uploaded things. Yeah, because on no
Or it's not on the canvas. It might be uploaded, but it's not linked on the canvas.
chapter 25. I'm looking at the chapter 25 discussion. I'm looking at the video.
Is there a second discussion in one video?
There is. Oh, the second one. Hold on. No. Okay, so let me check what's going on in here, okay? You
No
might have a
problem.
point in there, and I will post it back again in there, or probably we'll just not do the discussion for that part in there, okay? So we're going to remove it if that's the case, okay?
Gotcha.
Okay, see you guys on Monday, and please take care of this preparation, okay, and the quizzes and everything else, okay?
Thank you, Professor.
Okay, see you guys. Okay, the homework is part of your preparation, so do that too.
Of course.
Thank you.